All right. Nobody remarked that it wasn't recording. All right, but that explains why it wasn't swinging. All right, so very quickly, since I don't want to go through the whole long 5 minutes, this will be the 1 minute thing. We had A from before. The danger was we didn't know if somebody was telling the truth, and if they were lying and undervaluing stuff in the beginning, they could push a cutting point like this. We saw that the solution was to basically wrap the bar around and choose a random point to start and go from that point. And if we do something like that, that protects us from somebody lying. All right, so this was the two-person analysis. What happens if we have 3 people? So we want to divide among 3 people. So we'll consider say x1, x2, x3. So I'm going to use the same notation as the RentalHarmony paper. So the way they do this, simplexes will be 1, 2, 3. The stuff we were doing in the book was going to be 0, 1, 2. Doesn't really make much of a difference. And we'll have x1 plus x2 plus x3 equals 1. So we're dividing it among 3 people. What kind of divisions do you think we would like to get? If this is going to be acceptable.
Shouldn't everyone think they got at least a third?
Everyone should probably think they got at least a third. I don't know if I would go quite as far as they should think they got at least a third. I think it's close to that, but I don't think it should be at least a third. Because remember, we could have had that ridiculous situation in the first case where both people thought they got a quarter of the bar. But at least nobody thought they got a worse deal than someone else. So I think it's highly desirable that each person thinks they got at least a third. If you don't think you're getting at least a third, you should be thinking, somehow, this is not fair. I should be getting at least a third of the system. And if I'm not, then there's got to be a better way to do things. A lot of times you can fall into a bad equilibrium, where there might be no incentive for anybody to move out of it. Or maybe there would be an incentive for one player to move out, but not both players. So I think ideally, we would like each person to believe they got at least a third. But I don't think we can guarantee that initially. So you would want, maybe no one wants to switch. That seems like a really good condition. If, here's the 3 deals, which case would you like? Oh, I would take this case of all possibilities, and you'll take that case, and you'll take that case. Great, we all agree nobody wants the same case as someone else. That seems like a really good condition to go for something to seem fair. Have any of you taken a class in voting theory? I know Professor Vicelli often teaches this, where there's a lot of conditions you would want on voting, and it turns out that they're not all consistent. It's not possible to come up with a system that would satisfy all the conditions you want. How many of you have taken measure theory? Or heard the Banach-Tarski paradox? So there, you can't come up with a way to define volume that satisfies all the properties you would like it to have. There are a lot of times these conditions you want, they seem reasonable, but actually finding something in practice that implements them doesn't work. So what is, we want no one to have an incentive to switch. Do you think that would be a good enough condition that if we could find something like that, we should be happy? So if I give you a system where at the end of the day, no one is saying, I want to switch, does that seem like a good division? Yes. It may not be, unfortunately, the optimal division. And this goes back to the issue we had, where maybe both people feel that they're getting a quarter. Although in that case, when both people thought they were getting a quarter, in that case, would be happy to switch, because I think your part's worth 3/4, and you think my part's worth 3/4, so in that case, we would clearly switch. So in the case of two players, if there was a quarter for both, we would switch, but here, that might not happen. Question?
So we would have like x1, x2, x3, or x1 plus x2 plus x3 equals 1, and then maybe the whatever the scalar values might not equal 1 in that case. It's like you revalue your part.
Correct. So in some sense, think of it as you have utility functions for the three people on the bar, and different parts are valued differently. And we will assume people are being honest about their valuations.
I don't understand. If I get x1 in this valuation, and I think x1 is worth less than a third, then I think at least one of x2 and x3 is also worth more than a third.
Okay.
Right? That's true?
Yes, by the digital
has to be
principle.
more than a third.
One of them would have to, so then you would want to switch.
So I would want to switch.
Good. Excellent.
But we didn't talk about that in the last one either. So in that situation, we said that the 1/4 was fair, but we would definitely want to switch in that situation.
Correct. So I think the way we have to phrase it is, it would seem fair in that no one is getting more than another, but it would not be stable.
But it would be fair, but it wouldn't seem fair, because if you're from the perspective of the one who gets the 1/4, the other person's is worth more. The other person is worth more than a quarter. Does that make sense?
It makes sense. I mean, this is where it really comes down to how you define things. From your point of view, they're getting 3/4. From their point of view, they're getting 1/4.
And so from their point of view, they think you're getting a better deal.
Right.
So either way, even if the deal
Right.
is fair, no one thinks it's fair, so for all intents and purposes, it's not fair.
I will accept that as a friendly correction.
Right, we said that we would switch in that case.
So in that case, we said we would switch. And I think what Seth is saying is that we shouldn't consider this a fair deal if both people think they're getting 1/4. Is, in my mind, you're getting 3/4 worth. And so in my mind, I'm getting screwed. Even though I see from your perspective, you think it's also worth 1/4. It really comes down to we're mixing apples and oranges. And should I be if I'm looking at the division, should I look at the division just from my perspective? That seems maybe the best way to do it. Each person look at it from their perspective. From my perspective, I'm getting screwed. I'm getting 1/4. You're getting 3/4. So from my perspective, I don't see this as fair. If I then say, from my perspective, I see 1/4 for me, and putting myself in your shoes and trying to understand my opposition, I see my opposition thinks that they got 1/4. I believe opposition got far more than 1/4. I believe opposition got 3/4. But I know that they are mentally viewing it as 1/4. And so from their point of view, they do not see themselves as getting a great deal. They see themselves as getting the same deal as I am. And that's where it's a little tricky as to how do you want to interpret this. Because from their perspective, they are seeing themselves as getting this only 1/4.
But from their perspective, they're seeing that you got 3/4.
Yes, and we would immediately switch. We would immediately come to an agreement and saying, we both think, I can understand where things are. Why don't we both switch right now and both go up to 3/4? Yes.
Unless they value you not getting the full thing.
And then that becomes another thing to put in, is that a lot of times people are more concerned with making someone else suffer than getting something themselves. And there is a value attached to someone else's suffering. As a Red Sox fan, I am sometimes quite happy for both the Red Sox and the Yankees not to do well, to just keep the Yankees out of the playoffs. Schadenfreude is a great word. So one thing is, you probably do want each feels drop greater than or equal to 1/3 of the value. And we might even get this, so then the question would become is, if we had 3 cases, there would clearly be one that would be, if mine was valued by myself as under 1/3, at least one of the other 2 by myself would be valued as more than 1/3. What would happen with the other 2 people in terms of how they look at things? So we're going to see a system that will actually allow us to assign a division of this bar among 3 people that will have it so that nobody wants to switch. And so if nobody wants to switch, then that's going to imply that you've got at least 1/3. Because if one of the things was worth more than 1/3, you would clearly want to switch to that. So I think one might even imply 2. Because if you don't want to switch, you've got to have at least a third in your mind. Does that seem fair? Does that seem plausible? All right, so we're going to do two assumptions to do this. This is often done with cake division. All right, so normally the way this is phrased is you have some cake and you're trying to divide it among various people. And different people might like different parts of the cake. I think a half moon is a great example where you see the chocolate and the vanilla halves. Some people might like the pieces that have more frosting. Okay, you just have some quantity. And the two assumptions I'd like to make is you always prefer something to nothing. So there's never a negative utility for getting something. You always get a small positive utility if you get a little bit. So what this means is if you have a choice between getting nothing or getting something of your least desirable part, you will still choose your least desirable part. It's at least some asset that you have at your disposal. There are some times in life where you actually do not want to get anything. Anybody know an example where you would not want something?
Pile of trash.
Pile of trash. Excellent. I don't think anybody's really looking forward to, here's a pile of trash. I know when, I think it was when Barry Bonds was going for the home run record, the IRS issued a release that they would not count it as an asset by whoever got the ball that broke the record until it was sold. Because a lot of times when you win prizes on game shows, you do have to pay taxes on what you win. And so if you get a new car, you might not be able to afford the taxes of the new car that you've gotten. I think a lot of times game shows will give you the option of getting a cash settlement instead of the prize, because really they just want to advertise the product on TV. They don't care if you actually bring it home, but they just want to advertise it. But there could be times when, if you get something, there are additional costs to it. I will try another Seinfeld episode. Does anybody here watch Seinfeld? There's the great episode when they have, Jerry has tickets to the Super Bowl and is trying to convince George to come with him. And George is going through, how much is it going to cost me to use this free ticket that you're going to give me? Am I going to have to pay for my airfare? I'm going to have to pay for food and hotel. Yeah, this free ticket's going to cost me $1,500. For extra credit, who ends up going to the Super Bowl with the tickets? Cultural extra credit. Anybody know who the two people were? Newman and Tim Watley. Okay, so that's the first assumption. The second is preferences. So the paper writes it as the preferences are closed. What this basically means is that, think of it as continuous. That as you keep getting more, you're not going to all of a sudden instantaneously flip. If you prefer something and you keep adding more to it, you're going to still prefer it. As you go down, it's going to be continuous until you might finally get to that one point where it'll now be equal with something else. We're not going to be hopping back and forth in terms of what goes on. Okay, so what we want to do is we want to prove that there's a way to do the division. And we're going to use Sperner's algorithm. Sperner two-tier division. There are a lot of examples used in the paper. The more interesting one, it's a little bit more involved to explain, is the roommate problem. Again, I've mentioned this because this could actually apply to several of you. So if you are thinking of sharing an apartment with people next year, look at this part of the paper carefully. You will have a couple of different rooms, and different people will value the rooms differently. And so the question is, how do you assign the rent so that everybody thinks it's fair, but the people who are getting the better rooms pay a little bit more? And of course, what's interesting is somebody might value a room highly that you don't value highly. It has a nice application of duality. So we'd seen duality earlier in the semester when we were looking at bounds for how good things can be. This is another place where duality comes into place. All right, so we have three people. What do you think the names of the three people are?
Adam, Larry, and Curly.
Well, we could do Larry, Moe, and Curly. They usually do Alice, Bob, and Charlie. Do people want to do Larry, Moe, and Curly? Or do you want to do Alice, Bob, and Charlie? ABC. Anybody ever watch Family Feud? One of my favorite episodes is in Fast Money, one person got over 200 by herself as the first person. So they decided to have fun with her partner. And they said, we're going to just pretend you did horribly. And I'm going to just have fun and I'm going to just ask ridiculous questions to the next person. And so they said, okay, your partner didn't do too well. She got you like 24 points. I think you can do it, though, but you're going to have to work hard. Ready? And then the first question was, there were three stooges, Larry, Moe, and Curly. What was Curly's wife's name? So I'll put up the clip. They were interesting questions. Why are we going to use Alice, Bob, and Charlie rather than Larry, Moe, and Curly? Why are we using Alice, Bob, and Charlie?
It's easy to abbreviate. ABC is.
Well, I mean, Larry, Moe, and Curly is LMC. It's also easy to abbreviate. It's easy because they're consecutive. They're in order at the start of the alphabet. So the way it starts is we draw a big triangle. And then we're going to keep doing smaller and smaller and smaller subdivisions. So the first subdivision, would just be like this. And then if we were to do another level, you would go like this. Okay. And we keep going. And then I just want to match, I think it's A, B, C. Oh, they did it this way. Wow. I did hit A up here, B down here, and C over here. Okay. And then, so A, this way. Wow. So C, B. Then over here, they're going to put this as an A. Over here, this will be a B. And this will be a C. Anybody figure out what's going to go here? C. What will go here? B. Excellent. What goes here? A. What goes here? A. So is this working? A, B, C.
It's going to fail at the bottom right.
Yeah, so I'm saying, do we do a mistake? Okay, so okay. I think the problem was I drew those last lines too soon. All right, so we'll have to go down like this. All right. So A, C, and then this would become a B. This would become an A. This would become a C. This would become a B, and this would become a C. Okay. And then if we were to do the next one, we would have a C coming down from here. That would force an A to be over here, and then that would force a B to be over here. So what we're doing is we're putting in a labeling such that every triangle has all three labels. And so the question is this always doable? Well, we really just need to proceed by induction. If we've labeled all the way down to here, can we do another row? So the mistake I was making was I was assuming that we could actually specify the corners ahead of time. We can't specify the corners ahead of time. They have to be filled in. So let's assume we've gone by induction. then we have some kind of row like this. You then need to prove that you can always add another row so that every triangle has all three labels. All right. I'm going to leave that as an exercise to do by induction. So all subtriangles have three distinct labels. So that's a nice thing to try to do, yes?
Are you counting larger triangles that aren't the full triangle as subtriangles?
The subtriangles all have the same size.
Okay,
It's
so
all the
there's
same.
not like a set of 4 of those is not.
Correct. We're not forming a super triangle. And what we're really going to do is we're going to try to do Sperner's lemma. And so Sperner's lemma is going to tell us there's going to be a triangle that has 3 distinct labels. So that should look like this is not a hard application of Sperner's lemma. Yes?
Also, didn't Sperner's lemma require that all the ones on the edge
Yes.
were the same?
Correct.
And not.
Correct. So Sperner's lemma says everything on this edge would have to be BC, everything on this edge would have to be AC, and everything on this one would have to be AB. So I cannot apply Sperner's lemma directly to this triangle. I also really don't need to apply Sperner's lemma directly to this triangle. It's not that hard to prove there exists a subtriangle labeled ABC, because by construction, every subtriangle is labeled ABC. So I'm not going to apply Sperner's lemma to this. What I'm really going to do, and this is where it would be so much nicer in a couple of years when we would have this 3-dimensional board, is there'll be another triangle on top of this. And that triangle on top of it, I'm going to be assigning labels to the vertices. And what the A, B, and C will determine is who gets to speak at that time. So think of it as, if I'm at this vertex, I'm going to have some division of the bar. And person B gets to choose which of the 3 pieces B wants. If I'm over here, B gets to choose. If I'm over here, A gets to choose. And we can write any point here as basically x1, x2, x3, and they're going to sum. So over here, this would be the point 1, 0, 0. This would be the point 0, 1, 0, and this would be the point 0, 0, 1. So along here, that's going to be all the places where x1 equals 0. Are people fine with me using x1, x2, x3, which is the notation of the paper, as opposed to x0, x1, x2? Okay. So this is all the points where x0 equals 0. Over here, these are all, oh, no, not x0, x1 equals 0. I'm not fine with it. Over here, this is all the places where x1, x2 equals 0. And these are all the places where x3 equals 0. All right, so now let's look at our triangle. So I started off with a big triangle like this. Okay, I think that's the same triangle. So now it's person B's turn to choose. Does person B want the first piece, the second piece, or the third piece? Which piece does B want?
I mean, don't we need to know the valuation function to know that?
Not really. How much is the first piece equal to? 1. The whole thing. So I've divided up into 3 pieces. The first piece is everything, and the next 2 pieces are nothing. Which piece do you want? This is not the bag of trash.
First piece.
First piece, right? B is clearly going to choose the first piece over here. Over here, C gets to choose. Which piece is C going to choose? Second piece. The second piece is everything. Over here, A gets to choose. Which piece is A going to choose? Third piece. All right. Now this is beginning to look a lot like Sperner. Let's look at what's going on along the bottom. Would anybody ever choose the third piece? No. Why would no one choose the third piece on the bottom?
It's worth nothing.
It's worth nothing. We have made the assumption that something is better than nothing. I like calling this the bag of garbage assumption. We are not dividing up a bag of garbage. It is a positive quantity. It's a goodness. It's something you want. No one would take the third piece down here. Now what's interesting is the labels alternate between C, A, and B, and C, A, and B could value things differently. So it's not necessarily the case that it's always going to be ones up to some point and then twos from that point onward, because things could be valued differently. Maybe persons, B and C really love the stuff in the beginning and hate the stuff at the end, and A is the opposite. So maybe C would also choose a 1, and then A would choose a 2, and then B might choose a 1 again. If it was the same person on the bottom the whole time, then I would expect that it would be all 1s up until some point, and then it would be all 2s from that point onward. But because they're alternating, they're different people. I would expect some kind of continuity assumption that if I have B twice, if B prefers piece 1 over here, B should be preferring piece 1 over here because there's even more of it. Right? So if I had an even longer triangle, there would be some correlations among stuff like this. In Sperner's lemma, we didn't have any correlations. Should we be worried? No. Sperner's lemma says no matter what labeling you will have a triangle with 3 distinct labels. The fact that the labels are somewhat correlated just makes it a little bit easier, maybe. All right, let's look at what's going to happen along this edge. What's never going to be chosen? 1. Never going to choose a 1. So now we have A. Maybe A loves 3, so A will go up to 3. B hates 3, so B will go to 2. And C maybe also hates it. And then similarly over here, we're not going to have any 2s. Maybe it's all 1s. And now we fill in all the stuff on the inside. Could there be some dependencies in terms of how we fill things in? Possibly. I wouldn't be surprised. But we don't need to worry about that. So we know that there's got to be a triangle that has all 3 labels. So I can just put in my labels any way I want. 1, 3, 2. And here's my triangle. If the mesh was extremely fine, is there much of a difference between these 3 points? These 3 points would be almost the same. This would be x1, x2, x3, x1 prime, x2 prime, x3 prime, x1 double prime, x2 double prime, x3 double prime. And it would be almost equal. And so what we're saying is, in that division, here, each triangle has 3 different labels. So this would be B, C, and A. And what we'd be saying is, in this division, person B prefers 2. Here, person C prefers 3. It's technically a slightly different division than what B was looking at, but in the limit, they're going to be essentially the same. And over here, person A prefers 1. So in the limit, this is going to converge to one point, X, Y, Z. And at that point, by continuity, B will prefer part 2. Because it's a limit, B's preference could now be tied maybe with something else. Maybe B could equally prefer 2 and 3, but that's fine. B will still prefer 2. Or at least consider 2 equivalent. Similarly, C would feel that way about 3, A would feel that way about 1. So this proves the existence of a fair division. And it actually gives you a way to find it. The paper then goes through some additional details as to how you could possibly walk through the tree to find where that point is. But you can make these meshes now, and you can come up with a nice way to divide things. And at this point, does anybody have an incentive to switch? No. And you're making your decision irrespective of what other people value. I will leave it to you as an exercise to think, if you lie about your valuation, can you use that to move where things are in the tree? We saw the last time that if somebody lies, they could actually change the point we end up at. Is it possible to do that here? If I'm person A, if I lie about how happy I am here, well, this would no longer be a 1, 2, 3 triangle. And I could push the 1, 2, 3 triangle elsewhere. So I unfortunately do not have too much experience with lying and falsehoods and stuff like that, so I am not prepared to teach you how to do stuff like that. I apologize. But it's a great topic to look at when you put out a negotiating position that is not the one you truly care about. Okay? Any questions about this? I just thought that this was a really nice application of Stirner's lemma, in that you can see it's being used for problems you care about. The generalization to roommates is not too bad. It's in the paper. And I like the idea of having one tree above the other tree. That when you start putting down the names, it's not the spurner that you're going to be doing. It's just setting you up for the spurner. Okay. So we have 10 minutes left. And so what I thought I would do for the last few minutes is talk about how we might set up the divorce problem as a linear programming problem. It's just nice to see how you can do things like this. And if you can think rationally about the stuff now, then maybe later in life, if you need to do it, you can look at it calmly. Linear divorce. This doesn't mean divorcing your wives one at a time or your husbands one at a time. How would we set up the divorce problem as a linear program? What do you think my parameters are? What do you think my variables are? So what are the parameters? Nobody can think of any parameters for, yes?
Are we thinking of it as a bar still, or items?
So I think I made this comment last time that, again, things are fine at home, but, for the sake of argument, let's say Liz and I decide we've had enough. Kayla's 7 years old, Cameron is 9. That's 16 years of kids. We're not going to split them up, so each of us get 8 years of kid existence and, cut Cameron off like that. Especially since he has a soccer tournament tomorrow. So I don't think a bar is a good analogy, a good starting point for something like this.
So assets and preferences?
Yeah, assets and preferences. So what do you want to assume about the assets?
They're finite and discrete.
So it would be wonderful to assume finite and discrete assets. So we have assets, A1, A2, AN. For most things, we can make the assets discrete. If you have money in the bank, it's a finite amount of money. We can just look at it in dollars and cents. Can you give me an example of an issue with this? Or can we do this for everything? Is there anything you think that you cannot make as a discrete item? So, let's think about big assets you might have. A house. You could split the house as well as you could have maybe the house and the furniture. And then your different things in the house, you could have them in small individual assets, and then you could have the entire house. You could even, if you want, have constraints that certain assets must go together. Well, if the assets must go together, what can you do?
Make it one asset.
Make it one asset. Right? If the kitchen and the living room must go together, okay, you get the kitchen, I get the living room, and we're going to sell the dining room. You can't do something like this. You might just say one person gets the house. the money is really nice for something like this because that's okay. If somebody gets the house, then somebody else gets a lot more money. And now we have preferences. Maybe H1, H2, HN. This is the husband's preferences, and wife 1, wife 2, wife N. That's the wife's preferences. Anything else we need? And again, there is a danger of lying about your preferences to influence. Anybody ever trade baseball cards? Did you all? I won't ask publicly if you were always honest with your friends as to how much you valued certain cards in trades. So there is a huge incentive to lie. Yes.
Could you, instead of valuing, like, you stipulate like a ranking somehow? Like, it seems like that would protect against someone misvaluing us.
Okay, so you could try to do a ranking, and then
But then there's some assets they value way more than.
exactly, and so it's not necessarily a linear ranking. It's an interesting problem about how to deal with an issue like this. For now, let's make the assumption that they value things fairly. I do know of amicable divorces. We'll make the assumption that this is an amicable divorce, and they really just want to part ways as fairly as possible. Okay, any variables we would need for this problem? What should our variables be? Yes?
Would you like a binary variable?
Yeah.
So x, like xi is equal to 1 if like, husband receives the item.
If husband gets I, 0 if wife gets I. And what I might just do, just for convenience, is yi is equal to, I just do 1 minus xi? 1 minus xi. So now, if we just do something like this, we can easily record what the husband gets and what the wife gets. So, the husband gets, so it would be a sum of hi xi, wife gets the sum of wi yi. Are there any constraints? Can anybody think of any constraints? Yes?
Well, don't the xi's and yi's need to sum to n, or is that inherent in the...
Well, if xi is 1, yi is 0, and if xi is 0, yi is 1. So xi plus yi is always equal to 1. Somebody gets all of asset I. So by using these binary variables, we force it to be a situation where all the assets are allocated. And this is interesting. Do you want to allocate all the assets? That could cause problems. It could be that maybe you can't quite make it perfectly even if all the assets are allocated. And maybe you should donate some of the assets to the state. I think it's not unreasonable to say we want all the, they want the stuff to be divided amongst themselves, not going back to the Commonwealth. What do you think the objective function should be? It's got to be linear.
Maybe I can minimize the difference between the two sums.
All right, and just for simplicity, I'll call this, I'll call that H, and I'll call that W. So you want to minimize, yes, thank you. Without the absolute value, how do you minimize this?
The wife everything.
You give the wife everything, all right? I want to be very careful. I do not think that it's fair that one person gets everything. And so I do strongly suggest we put in absolute values so we do not give all the resources to just one of the two players. Does this seem like a fair way to minimize, a fair quantity to minimize? This is a really straightforward linear programming problem. All you need to do is you need to enumerate your assets and state your preferences. If you want, as a nice exercise, write this down. Do this as a computer program. Put down a couple of assets and see what would happen. And then for fun, see what happens if you lie about your valuation. And see how much you can influence things in terms of how much you can get. Yes?
Is it possible that like 2 or 3 assets are just valued by both like so much greater that like passing one of them would just like inherit the like forever sway who won or like who got the most?
Yes. And so this is the problem when you have discrete things. It's wonderful if you have a huge cash reserve, because then you can basically start assigning cash to balance things. So what would we do if there's like one huge asset like the house, and then that's essentially all we have? We have the house, and we have a game book from when the Red Sox won the World Series in 2004 and when the Cubs won it in 2016. They were opposite sports teams, and those are the only 3 things we have. So one person gets the house, and maybe the other people, yes?
You had a mortgage on the house.
That's exactly what you would have to do. Is in a situation like this, you would want to add another level of sophistication where certain assets would have to be converted to cash. And so a lot of times in divorce, both people might want the house, but the only fair thing to do is to actually put the house on the market. And sadly, you often may not be able to get somebody to pay what you think the house is worth. And so you could take a hit like that. But one possibility is that if you have a situation where that absolute value, that minimum, is too far from 0, the solution is to take some of the big assets, convert them to cash.
So, don't we need some kind of constraint on the preferences so that they're on the same scale? So, like, have them having.
Oh yes, yes. We should have them sum to 1.
Yeah.
Yes, that's a good constraint. So basically, we're splitting how much we value the entire collection among the n assets. Yes, that is a good constraint. So we would want the sum of hi equals the sum of wi equals 1. Right. So I think this is a good place to stop. Please, hopefully, never use this, or at least never use this for divorces.